Now it's time for the next lecture. The speaker is Mr. Koichi Sasada. He developed the ERB virtual machine for Ruby when he was in college. In 2007, it was adapted for Ruby 1.9. As a Ruby committer, he was engaged in high-speed language programming and performance improvement of virtual machine and garbage collection, implementation of concurrent and parallel processing. Currently, he works for Stores Corporation. He also serves as a board member of Ruby Association, and also he has a PhD for information science. So he will talk about concurrent and parallel programming by Ruby. Could you please go ahead? Thank you. Thank you. Good afternoon. I am Sasada from Stores Corporation. I would like to talk about concurrent and parallel programming by Ruby. So there are several mechanisms for Ruby for concurrent and parallel programming. So I would like to briefly explain that. And in this kind of topic, synchronization of the common data is often a challenge. You may think you'd better not do that, or if you do, there are some methods. So that's another topic I would like to talk. And this is my self-introduction. I work for Stores Corporation, and I am Ruby interpreter developer. And Stores Incorporation supports digitalization of stores, and I learned it for the first time when I joined the company. So the stores, shops are digitalized. That's supported by our company. And since the company uses Ruby, so I was engaged in Ruby development. Today, I would like to talk about concurrent and parallel programming, which I'm engaged in, and I have been working to support this. So I would like to talk about the basics. So my talk will not be too complicated. Talking about programming, it's ABC task is assigned to computer. That's what programming means. And ABC. In this sequence, task should be done. Then, in this case, sequential programming, one by one. So this is the sequence we order to the computer. Next one, parallel programming. So ABC, not in order. So any order, anything, okay. ABC should be done simultaneously, like when CPU is a multi-core processor, physically the several processing can be done. Then ABC can be done in simultaneously so that the total time of processing should be shorter. So that is parallel processing. So the purpose is make it quick. Next, the concurrent processing is like ABC. There are 3 tasks, and so the ending time is this the assigned. So the order is up to Ruby interpreter. So in this concurrent processing, so it can be parallel and non-parallel, okay. In case there's just one PCU, it can be done sequentially. Or in this case, this C, like a C stops because of IU. On such occasion, then what can be done? Then B can be done, and that's judged by interpreter. Then the machine switch to B. So that kind of work will be done. So that the system to support concurrent processing. So this is the summary. So sequential programming, the sequence is determined, and A, then B followed by C. So if human being write this, it's like this. And in case of concurrent programming, A and B and C, you don't have to worry about the order. Then it can be done anyway. Then among the concurrent programming, the same time simultaneously 3 to be performed. so that time needed will be 30%. That's parallel. So concurrent and parallel. So I would like to use these wording with the definition I talked about. Seki-san already talked about something. In this year's Ruby conference 2023, he talked about this, and I remember this, and let me quote. So this kind of concurrent and parallel program, there are a lot in the world. I think this is true because Seki-san said that sequential programming and sequential processing is rather a special case. So concurrent and parallel programming support is very important, and I'm working to improve that support. In Ruby, what kind of tool do we have? Here, you can see the Ruby 2 point something. Up until 3 years ago, there's a multi-process, thread, and fiber. There are 3 tools were available, and each of them have features. So according to what you want to do, you can decide which tool you should use. Okay, talking about multi-process. In order to do multi-processing, there are a lot of tools available. So process class can be used, or DLBD developed by Seki-san, or these days, just recently, the Rails can be used. The Mark II jobs, then Sidekick can work behind the scene. And also Unicorn can be used so that with the multi-process, the several process can be made, and that can process web requests. So that kind of configuration can be used in this case. The feature about this is that parallel processing is possible, and the data share is read-only. So it's hard to have a cross communication, but you don't have to communicate a lot. Then each is isolated and a clean condition. So if some problem happens, that process is killed, and the whole system will be okay. On the other hand, OS process management is necessary. So that's quite cumbersome. Therefore, this kind of tool can be used. I think it's best to have tools to do that when you want to manage the OS process. As to multi-thread, thread class can be used. Recently, or I'm not sure, Puma. If you use Puma, you can handle web requests through multi-thread. As to concurrent Ruby, this is a mechanism to support thread programming. This is also released, so I think you can fully utilize this kind of thing. In case of C Ruby, so it is just a concurrent processing, not parallel. So in case of web request, some read occurs, another request can be processed. All the data can be shared among threads. So good news is that there are less memory consumption. However, difficulty level of programming, because the data is shared among threads. So read and write. If reading and writing is done at the same time, then problem could occur. That's one negative aspect. If we want to make it perfect, then programming difficulty level becomes higher. So I think thread programming is complicated, so you'd better not do that if you are not an expert. As to C Ruby, so when you have the one Ruby thread, one native thread, like a Windows thread or a B thread, must be made. So if you make 10,000 threads, then system will explode, or explosion is too much to say. Maybe system becomes very slow. So you'd better, and it's heavy, system becomes heavy to deal with. Rather than making so many process, making threads can be lighter, but I think it's really difficult to make so many threads. Fibers. In other programming language, coroutine is a name used. So the shifting or changing over, so shift to what should be written, and it's all can be written, but this is a good and also cumbersome at the same time. And it can be used only for memory. So in the operating system, thread making is really cumbersome, but you can get rid of this kind of difficulty. So the only when process parallel processing and context switching, a process and thread automatic, however fiber manual. And the fiber is the best when it comes to the generation management, because from Ruby 3.0, Raptor and schedule have been added. Let me talk about that. As to fiber scheduler, Falcon, the same as Rack. No, the same layer as Puma, and it's a web application server. And async fiber scheduler implementation can be used, and very light web application writing is available. So this is the type of the software. What I'm talking about is that fiber can be used manually. So you have to manually write which time you are going to switch. But that can be written by Ruby. So it's a very convenient mechanism which can be introduced from Ruby 3.0. So writing, if for ordinary people, like a raised application writer, have difficulty of reading, therefore async is released. So I think it's better to use async. So by using async, fiber-based concurrency can be handled, and so far you might have worked on the fiber, like the switching manually, but that can be done automatically. And it's implemented with async. In comparison with threads, it's good because fiber is much lighter. So it's light. That's a good thing. So this is a merit of fiber schedule, and I think it's comfortable, just like using thread. As to Raptor, Ruby 3.0 had a Raptor. Synchronization should be written or read. If you want to that, synchronization is necessary, but you don't want to do that, so it cannot be shared anymore. So the number of the objects in which data can be shared will be quite limited. So that the synchronization problem can be avoided. However, programming model is different, so user application should be rewrite or library should be rewritten. So it's not penetrated the market yet. As to the data sharing, because of this restriction, the concurrent and parallel processing is okay. In the past, it works only in thread. However, when it comes to Raptor, the several Raptor can work together at the same time. And you can see Raptor and fiber schedule which have been added. So when you fiber scheduler, generation management cost is good and context switchover is automatic. Therefore, in comparison with thread, this is the difference. So generation management is much lighter. The Raptor, the parallel processing is available. Now, are we going to have addition of them? From Ruby 3.3, thread will be made lighter so that M&M scheduler was introduced by us. How are we going to use it? Thread. In making thread, the environmental variable can be designated to start a problem. Then thread implementation, like a native thread 1 per Ruby thread 1, that's implementation. But by using user level thread, it will be much lighter. So lower layer implementation is just like we do with the thread. So by making MM schedule, the generation management cost is lower. So theoretically, it's similar to fiber scheduler. So by using MM thread, cost for the generation management is low, like a fiber, theoretically. So maybe I will talk more detail later. So theoretically, I think this is a summarization. So by using thread or fiber scheduler, no difference that we are aiming at, and Raptor can be right, and I think we are targeting that situation.
This is one example from the benchmark result. Empty concurrent tasks, 10,000 empty tasks. So the task is finished very quickly. And so we can only look at the generation overhead for sequential processing, 10,000 loops, almost nil time required. But with the use of fiber, a little bit of overhead occurs. For threads, a little bit overheads. And the fiber scheduler, overhead is higher than fiber scheduler manual, however, quite small in comparison to threads. And from Ruby 3.3 scheduler, in comparison to thread, it's much faster. For Raptors, 10,000 empty task with Raptors, very slow. This is something we need to pay further attention to. So not empty task. What about this? 4,000 data download from one URL. A sequential 2 seconds. With async, with the appropriate handling of I/O, a lot faster, but twice as fast as sequential. This is the fastest one at the moment. And with threads, thread management overhead is higher than sequential, but with scheduler added, a lot faster. The blue is the generation cost, almost nil generation cost with the threads with scheduler. It seems that it works faster. In comparison to async, it's a bit slower, but with the Ruby 3.3 released in December, by that time we hope they'll be able to do the good tuning for threads with scheduler. So what concurrency primitive do we have with Ruby is what I have gone through. And in the next release of Ruby, I showed you some of the improvements you might want to expect to see. Now, thread API and synchronization, some further discussion. Well, time is running out. I don't have enough time, so I cannot go into the details, but some ideas. Thread generation with Ruby is accomplished easily with this writing, and thread waiting for thread, thread value or thread join allow you to wait for thread completion or thread queue or size recovery can also be used. And for error handling, it's a bit detailed, but if you want to go through squarely, you need to write a error handling. And thread interruption. When thread is running, if you want to interrupt, there is a way to do so. So those are the primitive with thread. What about thread synchronization? This is the next piece I'd like to take you through. First, we create a person class. A point of a point card. There is a point anyhow with the class person, and we created an object and koichi. And right now point is 0. This is an example of threads competing with each other. Thread 1 and thread 2 almost simultaneously want to add points. That are the requests issued simultaneously. T1 wants to add 10, and the T2 thread would like to add 20 as points, and the total should be 30. if it is done sequentially, right now it's 0, and adding 10 means 10. So add 10. And when the value is 10, thread 2 load the point and reads the current value as 10, and thread 2 want to add 20, and 10 plus 20 makes 30. So the point here will be 30 at the end. Something strange has happened. Let me redo this. It's gone. So you get the right value, 30, which is good. So that's the usual program. No problem took place. But something odd happens when there are some mistakes. Thread 1 loads 10. The current value was 0, so the total right now is 10. And before writing by thread 2, before written by thread 1 as 10, and if thread asks what the value right now, and if the value is still 0, then thread 2 adds 20, and on the other hand, thread 1 wants to write in 10, and thread 2 writes 20. So at the end of the day, in this case, 20 is written after 10 is there. So it must be 30, but actually 20 is written, and that is the data race between threads. In order to avoid this, we need to use a lock mechanism, as you know. In Ruby, we use a mutex. Within synchronization, when the block is executed, a lock is placed, write something, and then unlock. During locking is working, thread 2 may want to modify the value, as in the previous case, but thread 2 cannot get the lock, so unlock must take place first before T2 writes. So processing number 7 is delayed. As a result, the right value 30 can be written. So this is a textbook-like data competition case between threads. But what is the problem? We tend to inevitably forget to use lock. The previous case was a simple case. So if you look at it closely, the programmer may notice that the lock has been forgotten. But if the problem is too large, it's really hard to recognize that lock has been forgotten inadvertently. Lock should have been done, but that has been forgotten inadvertently. Also, even if there is a problem difficult to notice in certain cases, the previous example is that the problem took place when a strange timing was used for writing in, and this is 1 out of 1 million, and such a thing cannot be detected in a test program. And it's really hard that the number is wrong. For instance, it is 20 instead of 30. If the program stops, then you might notice something is going on. But maybe you do not notice if the difference was only 10 points, like the case between 20 and 30. So it's really hard to notice such a problem if the program is too complicated. In the case of Rust, which has a type, you can force lock with the use of type. but such a type cannot be is difficult to use in Ruby. And another issue is that it is difficult to combine multiple locks. Or you may want to move the points. Two people, Koichi and Yuki, each one of them has 100 points. And thread 1 want to move the points from Koichi to Yuki, and thread 2 want to move the points the other way around. And locking is necessary, and each one may use a lock. T1 and T2 uses locks for the purpose consistency, but at the bad timing, the following can take place. After T1 gets a lock, and T2 try to lock again. So after T2 gets the lock, T1 tries to lock. 6 can never take place. Yuki's lock is there, and in 4, the lock cannot be placed. So this is a competition between two locks, and no further progress can take place. And this is called the deadlock situation. And such a problem can take place more or less easily. What is the solution? There can be multiple solutions to overcome this problem. But after all, such a problem should not be treated in Ruby. Concurrent processing shouldn't be written, or you may just leave it to external database. But in writing a program, such a problem does take place. So one solution is transactional memory. If you are writing a database, as pessimistic lock can take place. In that case, the other party will not be able to modify the data. And optimistic lock is that we assume that data lock wouldn't take place, and if take place, you would just redo again. So optimistic lock is something that is used in transactional memory synchronization. A few years ago, I made a transactional memory, and T-var is the implementation, and it is called the Rakta T-var, and this is a transactional memory usable between Raktas. What it does is as follows. If you have such a value, atomically, that block is a transaction. Within that block, the value can be accessed. But there should be a commit at the end of the block, and if there is any competition, that block should be redone. And this is a concept which is often done in database. What is good about this is the transactional memory outside the block, the value cannot be accessed. So we just do not forget into transactional memory. By mechanism, you cannot forget to lock, and also multiple locks. They may come to a deadlock more or less easily, but with the use of atomically nesting, at the end when the commit is done, and if there is a conflict, you redo it, but you can redo it from the first block. By so doing, you can write a workable one. So it's easy to program, and also a deadlock will not take place. So this is the synchronization method I often prefer. I have gone through various tools and mechanisms for parallel and concurrent processing for Ruby, and for Ruby 3.3 we hope that more improvement can be made with the introduction of M and scheduler, and synchronization is a difficult issue in certain cases, and I recommend that you do not do this, and in the case you might want to use a transactional memory. Thank you very much for your attention.
Thank you very much. Well, we would like to entertain some questions from the floor. If you have questions, could you please raise your hand? I think it's so silent. Well, please use a microphone. There is a person who wants to ask questions. Very slowly, the microphone has reached to him. Thank you very much for your presentation. The transactional memory was the last topic. So as a performance, is it practicable in terms of performance? Well, I think it's up to aborting rate. So without abortion, it's good. So only reading is okay. Or if there's any conflict, and pessimistic look is faster. So that's my impression. So rather than performance, I think that errorless program is more valuable. That's my feeling. Therefore, transactional memory is recommendable. Okay, thank you. Thank you very much. Any other questions?
Please. Open your eye. Addressing UI, is it? Do you know when that happens? There are some requests, and we are now reviewing. And expanding ecosystem is what is necessary, and would like to spend more time on that effort. So I haven't answered such pro requests. I would like to take on that. So it's possible. If you are determined to do it, I'm sure he will do it. There may be more questions, but it's time to thank the speaker. So please use other occasions and approach him on an individual basis. Please give a big hand to Mr. Sasada. Next speaker is Ms. Keiko Itakura with Medley. Before this, we would like to have a 10-minute break. The next presentation begins at 5:35. 5:35. Thank you. One information, Mr. Hashimoto Toshimitsu, you dropped something. Please come to the secretariat, room 303. We have something found for you.